Guys, attendance is on in case you have not put it yet. Okay, so I think there's no point waiting anymore. Let's start. Uh, by the way, the form that was sent to you for lab exam, most of the people have voted for 3rd and 10th July. So the two lab exams will be on 3rd and 10th July, and keep it in mind that both are compulsory, and they'll have like 50% of weightage of your overall lab, uh, whatever is right, whatever lab grade you will get. There'll be 50% of there'll be 50% of weightage for both of them. So I'm not giving you any what is it? There is no best K out of N thing this time, because there will be only two labs. So please keep this in mind that it's necessary for you guys to appear in both of them. And okay, so by the way, the lab problems that I have been giving you, I will share the solutions also, at least for the two I have already given. The third one I have to still prepare another problem. But the idea is you should see the solutions that I will share, because this is what I will expect when you appear in the lab. Okay, so don't feel, I've said this before also, that it's not a data structures or ITP lab. So the expectations are different. Okay, it's not really about achieving the functionality, it's about how you are achieving it. Okay, it's not just the end result, it's also about the process. Okay, let me start. How many are there now? 44. Okay, fine, I think that will be fine. Okay, so as I said, basically from now onwards, every week there will be some UML, very basic UML, and then along with that, there will be some system building skills. So this week, the system building skills we are having a look at is multi-threading. Okay, so now multi-threading is something that as a developer you will be required to use at many places. In fact, there might be certain languages where the multi-threading support is really really good, whereas some other languages might only have limited multi-threading support. But most of the modern languages do allow you to do multi-threading. So today we'll just get an idea of what multi-threading is, and in the next lecture I'll show you some coding examples, like if you want to do that in C and C++, what is the way to do that. But today just I have to cover certain basics before I can actually jump to the multi-threading part, because you guys have probably not yet been you guys haven't been exposed to the world of operating systems. I mean, I'm pretty sure whatever I told you in the previous semester, that is the only knowledge most of you will have. So it's more of an operating systems concept, so you'll need to know a little bit of the background before I can show you the code. So today it's about the concepts related. It's not theory, as in it's not design, but these are basically concepts related to operating systems. You will study all this when you study the course on operating systems. It should be later, sometime in your curriculum. I'm not sure what semester it would be, usually third, fourth semester, somewhere like that. Whenever you'll have operating systems, you'll study all these things in detail. but just to give you an idea of how threading works, I'm going to cover the very basics of it. So, first of all, there are two ITP lectures which are relevant for today's talk. Some part of today's lecture is from these two lectures. So, one of that was actually a digression lecture. Now, I understand that I could see the views on YouTube that people were not really interested in digression lectures. I did prepare, I think, a couple or something, maybe two or three digression lectures, but people were not really interested in digression. So because it was not a part of your syllabus, so there's a good chance that many of you have actually not seen that lecture. But in case you want to, the lecture is D2 from, so basically second digression lecture from ITP. So a good amount of content is coming from that lecture, but I assume most of you have not watched it, so we'll go through it anyhow. And if you remember the first few meetings in which we met, right? The first lecture, the second lecture, some part is also coming there from the second lecture, 0.2. Okay, so it is just to give you a revision, because this is not strictly programming. This is basically operating system and understanding how operating systems work, so that you can then continue to writing threads. So that lecture is 0.2. So if you would like to revise that lecture, that will be helpful as well. But there is some more content here, and so if you do not want to revise, I think it should be fine. So this is where we started off in that digression lecture. The idea is that whatever programs you run on your machines, okay, on your laptops, basically these programs, when they are executed, when they become a dynamic entity, okay, programs are something that you type, right? They are, in some ways, they are a static entity. Okay, you type the code, and then whatever is the output, that is the static entity that we call program. But the moment it starts executing, the moment it becomes alive, or the term that we often use is running, the moment it is running, it becomes a process. That is, it could be one or more, but in most cases it will be one process. Okay, and if you want to see how many processes are currently running on your system, and I'm assuming after constant nagging by me for maybe 1.5 semesters already, most of you are now operating either in some Linux based environment or some environment within Windows which is trying to emulate Linux, right? So I understand that the newer versions of Windows have some support for Linux. So the idea is that you have access to some, um, we call it asterisk Nix environments, right? So basically they are environments which are pretty much like Unix or Linux. So so if you are in any asterisk Nix environment, there is a command called top. Okay, if you type it on your screen, on your console, you'll see something like this. Okay, and what exactly is this? These are the currently running processes. You have to understand the term currently running. Okay, this is the exact dynamic screenshot of your system. Okay, this is not something that is in past. This is the current thing, right? So you with the help of top, you cannot know what processes were running on my system 2 hours back. No, that is like, this is the current scenario. This is exactly what is happening right now, and it gets updated frequently. I don't know what exactly is the update time, but I guess something like every second, every few seconds, so it gets updated. So whatever top shows, it is essentially the currently running processes on your machine. Now you might feel that I am only running maybe one or two applications at a time. Maybe only my browser is running, and maybe I just have another Microsoft Word or something like that opened up. But how is it that there are so many processes running? And that is the idea, that not all the processes that are running in your system, they run in the foreground as in something that you can see. There could be processes which are running in the background. Okay, these are processes which you see, which you really cannot see in the true sense, but they are still running. And that is the idea, that um, on any operating system, at a time there will be hundreds, maybe thousands of processes running. And even if you are not doing any tasks, there are still many processes which are running in the background. In this case, if you would like to know something more, for example, this particular column shows you the amount of CPU in percentage a particular process is taking. So you can see the processes and the amount of CPUs that they are hogging. And then this mem thing is there, which basically tells you the amount of RAM, primary memory, that this particular process is taking up. So this command, top command or top command, can show you the currently running processes on your system. So you should try it out sometime. There are some more things here. There are things like 1903 threads. We'll talk about threads soon. But the idea is, this top command, you should start using it. It's similar to the what is it called in Windows, task manager, right? I don't know what is it called in the newer versions of Windows, but the versions that I have used, Windows XP and Windows 7, uh, they used to have a an application called Task Manager, um, which you can on Mac you have Process Monitor. Okay, so it is in some ways an equivalent of that. It's just that it's a command line based version. So you guys might already know, but in case you don't, processes are basically units of execution that the operating system executes. Okay, so that is what I said, that you may write a hello world program. Okay, so it could be in C++, Java, any new language that you are learning. So what you write is just a program, but when the operating system starts executing it, it becomes a process. That is the difference between a program and a process. Now, any questions? Okay, sorry. So, so operating system, whenever it wants to create a new process, okay, there is a kind of process life cycle. Where is basically it doesn't really happen in an ad hoc fashion. There is a well-defined mechanism to manage a process. Okay, so the process that is to be executed, there are certain states before that this particular process goes through. Or you can say that from a program to something that is a running process, there are certain steps that go through. So all those steps are considered to be the part of starting a process. Okay, so whenever you initiate the execution of a program, certain things have to be done. Okay, and what are these things? Essentially, the operating system has to see if there is any space available within the main memory, because you all know that whatever, this is from your lecture 0.2, that whenever something has to be executed by your CPU, it has to be a part of it, the instructions must lie somewhere in your main memory. So if there is no space within main memory, at least in theory, you are not allowed, or you cannot create another new process, because there's just no place in the memory to put the instructions and then execute it, right? Of course, it doesn't work that way. There are ways in which the operating system can manage it. Okay, the operating system can create some space, and by putting something out and getting something in. I'm not going to discuss all those things. These are some things that you will study in operating systems course itself. But the idea is that there has to be some kind of tasks that must be performed by the operating system when a particular process is to be created. So once all those things are done, the process enters a state called ready state. Okay, so ready means it is now ready to be executed. So as soon as by the way, in most cases the number of CPUs that will be there on your machine will be limited as well, right? So it in the most general case it will be just one. But these days the computers are more powerful, so you'll at least have two, I would say. Maybe it's not even a it's not an anomaly even if your machine has four, for example. Okay, but the idea is whatever are the number of CPUs available to you, there is a good chance that they are currently executing codes from some other process. They are not yet free. So the ready state is essentially a state in which the process lies until it gets the CPU to execute. Okay, so this is the starting state where after all the bookkeeping has been done, the process goes into the ready state. Once the CPU, I'm assuming it to be a single CPU machine. So once the CPU is available and it gets allocated for execution of this process, the process comes into the running state. Okay, so now it has started executing the code that is there in as part of your program, that starts getting executed. Now, there are certain scenarios in which a particular process might enter the blocked state. Okay, the most common reason for a process to get blocked is for an IO request. IO request, as in, that whenever you write a program and wherever you write something like C in X or C in Y, right? What does it mean? It means that whatever execution has already happened, the execution should stop at that particular stage, and at this particular stage you are supposed to provide an input, some number, some string, something, right? And once you press enter, only then the execution should proceed, right? Your program basically halts whenever there is a request to take input from the user, for example. So this is an example of input output request, IO request. Okay, so whenever a particular process is executing, there is a good chance that it might have to be stopped, it might have to be paused for some kind of event. The most common event being input output. So if such a state if the process reaches such a state, we call it that we say that it is actually in the blocked state. Okay, now as soon as the input output request is over, the process again goes back into the ready state. So then from here, again it has to wait till the CPU is available and there is some mechanism through which it gets the CPU. So then once this blocking reason is resolved, it goes back into the ready state and waits for its turn to get the CPU, right? There are some categorizations which consider new and terminated as process states. So basically, new is the state where the process has just been entered, right? I mean, it's like a new request has come to create a process, so you call it the new state. And then similarly, once the process has completed, it goes into the terminated state. So it depends, right? The different types of texts that are available, it is only these three states that matter, but they also sometimes say that new and terminated are also two process states. By the way, any questions about the process life cycle? Is it clear what really happens when you execute a program? So we have already seen the actual execution part, right? We have seen it, how things are represented in assembly form or some kind of binary form, and then there is a program counter. It executes from one point to another, right? That we have discussed in ITP at length. But do you understand the overall process life cycle? How something that is typed by you becomes something that is currently executing. Okay, so this is the process life cycle. Any questions on this? Okay, so Now, just to give you and let me just pull this thing down. Mm, okay, so just to this we have seen um, a similar diagram when we were discussing the execution of the program. I told you that essentially there is some memory and there is some code. Within this code, the instructions are stored. Within this memory, the operands which are required for this code's execution are stored. Essentially, whatever variables you create in the program, they go in probably in this section, and then the program itself is here, and this whole memory is currently allocated. This is a chunk within the main memory, by the way, and this whole chunk of storage is allocated to a new process. So this is basically a very this is an oversimplified view of a process. That is the idea. That is exactly what you need to know. This is the code the operating system executes as part of running the process, and we have seen this at depth in lecture 0.2 from ITP. And this is not really C++ or C code. You have to understand that the actual language in which the program was written at this point of time, this code is agnostic to that programming language in which you wrote it. Okay, this is low level code. These are basically binary values, 0 1 1 0, something like this, right? So all those concepts that you studied in ITP, there is an operation code, there is a place to fetch the operand, all those things, right? So that kind of code is here. It's written here, right? And yeah, similar to what we saw in week 0, right? You guys already know what we saw in week 0. So now this memory, it hosts all the variables and constants, okay, that you all know. And there are we have discussed this in slight detail. I think if I'm not wrong, Avnish, in the lecture by Avnish, he actually told you many more things about these different types of memories, and how they play a role in programs execution. But anyhow, so you also know about that PC register, program counter register, right? Program counter tells the CPU the location of the next line of code that must be executed. That is what is the job of program counter. So yes, we have discussed program counter in week 0 as well. So this is basically how a typical process looks within the main memory. Okay, so there has to be some space allocated for it, and within that space we have to allocate some section where data resides. Data as in the variables, the constants that are defined in your program, and then the rest of the space is allocated to the code, the actual instructions that must be executed when the program when the program becomes a process. So we have discussed this at depth, so I have not gone into details, but any questions on this? I know it might be a little foggy for some of you because that was during week 0 of ITP. It wasn't in the week 0 of actually I should have written week 0 comma ITP. So that was the week 0 of ITP where we discussed all those things. Any queries? No? Okay. So now what exactly is the idea of multitasking? So now in the initial operating systems that were designed, they were in some ways they could only execute one process at a time. Okay, that was one of the limitations, right? You give them one program to execute, they will convert it into, let us say, a process. The process executes, the job is done. Okay, but most of the all I'm not even sure if there are any operating systems which are of that type today, but almost all, I would probably say all operating systems today perform multitasking. So what it really means is that they actually keep a set of processes alive simultaneously, right? So you saw those three process states, ready, running, and blocked, right? So there will be multiple processes at any point of time which will be in either of these any one of these three states. They are not terminated yet, for example, right? So there will be many processes in the system which will be in one of those three states, and that is what I mean when I say that a number of processes are alive simultaneously. Alive as in they are created, they are already I mean they are already being executed, and they are not yet terminated. So that is what I mean by alive. So this whole concept of executing multiple tasks simultaneously, that is in some ways known as multitasking. And how does the operating system actually do that? Assuming that there is just one CPU on your machine, the operating system picks one of them, executes it for some time, and then it puts it back in the ready state again, right? So now, assuming that your process is actually quite long, the program that you're trying to execute, it's a huge program. Um, it is quite possible that even though for you it might seem that the program uh, finished execution maybe within a fraction of a second, or at best a couple of seconds, but what really happens in the background is that this process did not execute continuously for, let us say, 1 second. Okay, it seldom happens. What really happens is this process would have executed for a few milliseconds or a few nanoseconds, then it would have been put back again in the ready state. Okay, and then some other process would have been given some time to execute, then that process would have been put in the ready state again, and then some other process, and then some other process. So essentially what we really see in most of the cases is that there are small time quantums, we call them quantums. Okay, so the quantums are essentially chunks of time. So what happens is the operating system executes processes by giving them small time quantums, okay, to execute. And as soon as the time quantum of a particular process expires, the operating system takes away the CPU access from this particular process and gives it to someone else. And this process, the one that was currently executing, it goes back into the ready state. So uh, at least at this stage, you can consider this to be some kind of a round robin scheduling. So let us say there are 5 processes, so they keep on sharing the CPU between themselves in some kind of a uh, so did my voice break in between? I could see that my my broadband is not doing well. Oh, okay, great. Great, great, great. Okay, so very good. So maybe the ping stopped working for a while for some reason. Anyhow, so what was I discussing? Yeah, so I was discussing this whole concept of time quantum. So what happens is um, the way this multitasking takes place is that the operating system allots the CPU to one process for some small amount of time. As soon as the time expires, or there is a request, or there is there is an event which occurs, because of which the process must be blocked. One example of such an event is an input output request. So either of these two happen, right? Either the time quantum expires, or there is an event because of which the process gets blocked. In either of these two cases, what will happen is the operating system will take away the CPU from this particular process and give it to someone else. So, and by the way, this switch from one process to another is so fast. Okay, we are talking about um, sub millisecond times. Okay, so this switch I okay. I just checked the chat. There is a delay. Is it? I think it should be fine now. It my ping says it is better now. Or okay, okay, fine, great. So yeah. So basically, the idea is something like this. You need. I mean, the processes which are there in your system, these processes, they share this particular CPU with each other, and the this sharing, this whole process of giving this CPU to one from another is so fast that for a naked eye it would look like all the processes are running simultaneously. Okay, and this is a kind of an illusion that your system gives you, even though it is not really the case that if you have one CPU, actually only one process can execute at a particular time. But because this switch is so fast, it might seem to you that you are able to run multiple programs, multiple applications simultaneously. But what is really happening is that it's a very fast switch between these processes. Okay, and uh, so what exactly is crucial now? Let us say my process had 100 instructions, let us just say. Okay, and in one particular quantum I was able to execute 25, the first 25 instructions, but right after that my quantum expired, right? So now the process has to be put in the ready state. When the next turn comes up, where should I start executing? I should start executing from instruction number 26, right? Not from the beginning. So this has to be stored somewhere, that I have already executed 25 instructions out of 100. Next time this process gets a chance to execute, start executing from instruction number 26. And how can I do that? In the simplest form, all I have to do is store the value of program counter. So whatever is the current value of program counter, whenever I take away the CPU from this particular process, if I store it somewhere, the next time I give this same process the CPU again, it is like restoring everything from the point it was stopped. Okay, so it will again, there are many other things that I have to restore. I have to restore the values of the different variables, registers, blah blah blah, everything. But yeah, in the simplest form, what you can say is, as soon as if I want to um, if I want to restore the state of a particular process while it was running, some amount of information can be stored somewhere, and from that information, during the next quantum, I can restore everything, and it will look as if the process was executing continuously. Any doubts on this? This is, by the way, a pictorial representation of the same thing. Let's say you have these processes P1, P2, and P3, and then this represents time quantums. So first, P1 was given the CPU, P2 and P3 were in the ready state. Then, as soon as the quantum expired, then the CPU goes to P2. The others are now in the ready state, and then it goes to P3. Something happens here, let us say an input output or something like that. So this particular uh, process P3 gets blocked. So here itself the CPU gets allocated to this one. This is a very simplistic view. Don't consider this to be technically accurate. This is just to give you an idea that what really is happening, that as soon as there is a blocking event, the CPU is taken away from the process and given to some other process, usually in a round robin fashion. That is the idea. Any questions on this? If you have already seen the digression lectures in ITP, all these things you should know. But I assume that many of you would have not seen it. So any questions on this? It's all clear. So you now understand what exactly is multitasking. The it's the idea where you keep multiple processes ready at any point of time. And so there is some question. The instructions are stored in memory. So it depends on what is to be done with it. So if the number of processes that I have, which I am currently executing, the number of active processes, if they are not too many in number, then they remain within the main memory. They are not supposed to be kicked out. They remain in the main memory, and when the quantum expires, that part of memory gets still remains occupied by that particular process, and when the next quantum comes in, same block is used for execution. But this might not happen all the time. If the number of processes that are supposed to be running in your system are far too many, what happens is that the operating system has to do some kind of optimizations. So in that case, what it might do is it might swap out a process. It's called as swap out. So basically, if a particular process is currently not executing, and in near future it is not required to execute it either, so let us say the time quantum that will be given to this process is it there is still a while before this process will get the quantum. So in that case, the operating system may actually free that part of the memory and give it to some other process. So in that case, what the operating system does is that a part of your hard drive, it is known as swap space. Okay, the swap space is a space which the operating system uses for its own purpose. It's a part of your hard drive that is not available to you. It is used up by your operating system. So so in such cases, what happens is the memory that was given to this particular process in the main memory, it gets written back to the hard drive. That part is cleared, and then it is allocated to another process. It is known as swapping. Okay, so you put something out and you bring something in. But again, these are advanced concepts. You will study about swapping when you study operating systems. Any more questions? So you now understand that in order to execute multiple processes, this is the mechanism that is put in place. Okay, so there is some memory associated with each process, and as long as you are able to store the state of a process, which as we discussed currently, the most important aspect is program counter, but there are some other things as well. So if as long as you are able to store this state of a process somewhere, you can stop executing it and give the CPU to someone else. This was all about processes. Okay, so now what are threads? So threads can be seen as lightweight processes. Okay, what exactly are lightweight processes? Or another way is you can consider processes as heavyweight threads. Both these terminologies are in use. Okay, some might call that threads are lightweight processes, and some others might call processes as heavyweight threads. They are just like different forms of the same thing. So now just imagine that there is a particular process which has multiple program counters. Okay, so now this might be slightly confusing for you, that how exactly is it possible for one process to have multiple program counters, right? So for a moment, just be with me. We'll come to such scenarios later, but let us assume that there is a process which has multiple program counters, and when such a process gets the CPU, it can choose to execute code pointed by any of these multiple program counters. Okay, so we say that such a process has multiple threads of execution, and out of which this process can pick anyone based on some policy to execute as the next instruction, right? So the operating system deals with the processes, and the process can deal with threads. So they can have one or more threads of execution. Okay. Again, this is not always true. Most of the operating systems these days, they also do it using threads only. But for our discussions, we will assume that threads and processes are different. Processes are at the higher level, and processes are directly managed by operating system. So it is the operating system who decides which process is going to execute at what point of time based on the time quantums. And within a process, I said that it is possible that the same process might have multiple program counters. So let us say if the process was given 50 milliseconds of time to execute, it can say I have three different program counters having three different threads of execution. I will divide 50 between them as 20, 20, and 10. Okay, so but that is at the level of the process. So just to give you an example of that same oversimplified process, now the process looks something like this. Okay, instead of having one common memory, you now have three compartments in this memory part, right, where the variables were stored. You remember the variables and the constants were stored. So now assume that you have three sections of these variables and constants. Okay, and they are independent of each other. Okay. Similarly, you have three program counters and three different sets of codes, and all this are part of the same program. So now you might actually wonder, why would I need something like this? So can any one of you come up with a scenario? Can any one of you think about a reason why I would need something like this, where the single process has three different sections like these? Any thoughts? Why would you need something like that? Anyone? You guys use, by the way, such applications all the time. In fact, we are using one right now. So can you like think, why would a process need more than one code sections, more than one set of variables, more than one program counter? Any thoughts? Okay, so we are currently using WebEx, right? And what are the things that WebEx give you? So first of all, there is an option for chatting, right? Someone just wrote a message to me, and the message was sent to everyone. At the same time, I am also presenting something to you. Okay, so I'm using my mouse pointer in this presentation slide. Okay, at the same time, I am also speaking something, and you are able to hear me, right? You understand that these three. Yes, right. So one simple example is WebEx, that these three are completely independent things, right? Uh, you know, being able to hear my voice, I can actually mute it or unmute it. So that is a completely different independent aspect. I can share or unshare my screen. That is a completely different aspect. And at the same time, I can send and receive chats. So at the same time, there are at least three different tasks that this WebEx is doing for us, right? And it's highly likely that at your operating system, it is just seen as one process. Okay, only there is just one process called WebEx. I'm just assuming it's WebEx. I'm using a browser. You might be using the WebEx application on your phone or your laptop. There's a good chance that only one process is running out there called WebEx, and all these three things are being done by the same process, right? But you can understand that the kind of code that will be written to handle these three will be significantly different from each other, and all these three pieces of code must run, I'm putting it in quotes, simultaneously, right? So how could this be possible? It could be possible if I allow the WebEx process to have, let us say, three different containers. There are three different program counters. There are three different sets of variables, and one section is handling the chat, one section is handling the the screen sharing part, and the third section is handling the audio part. Now can you understand why would a process need three different sections like this? Because it might have to do three different types of tasks at the same time. Is this part clear? If this part is clear, you now have the idea of why we need multi-threading. Okay, the first thing that you know, why did we need multitasking? So that we can run multiple applications simultaneously. And why do we need multi-threading? So that the same application can do multiple jobs at the same time. Is this part clear now? That what exactly, why do we have these three sections, and why, and you know, these three, and what exactly is this their significance? Why do we need it? What kind of things that we can do if we are given such liberty? Is this part clear? Any queries, any doubts on this? Because if this is clear, then from here onwards it is just you know, you should feel motivated that okay, I too want to write code which can handle two things at a time or three things at a time. Is this part clear? Any queries? Okay, so if this part is clear, then yeah, so we have already you know, talked about it, that basically each thread had its own program counter, each thread has its own code to execute, and by the way, these are all called threads of execution. And each thread has some memory which is dedicated towards it and not accessible to other threads. So basically they are like mini programs within a large program. Okay, they are independent of each other. They might run independent of each other. One's program counter might be here, other one's program counter might be here, the third one's program counter might be here. So they run independently of each other, and they provide three different facilities, three different features in your application, in your program. Okay, and by the way, there is some common memory too between all these threads, so these threads can communicate with each other. So that is the difference between, let us say, a thread and a process. These are lightweight things, so I can do far more things here. So communicating from one thread to another is usually cheaper in terms of the amount of time it will take, as compared to communicating from one process to another process, right? So there is some common memory which can be used for communication as well. uh, yeah, let's not go into that. So how do we do these things, whatever we have just talked about, in C and C++? So there is something known as POSIX, portable operating system interface. It is a set of standards. They provide apis are basically application programming interfaces, and they provide it for crucial tasks, so things like managing processes, managing as in creating processes, you know, managing their whole life cycle, the process life cycle that we just saw. They can be used for performing networking. We will use POSIX POSIX sockets later in this course to do some basic networking, and they can be used for creating threads. Okay, they are supposed to be portable across platforms, but they are mostly popular on these Nix systems. I don't think Microsoft likes these guys much. So there are different POSIX modules for different tasks. There is one called POSIX threads or p threads that we are going to use. There is a header file called pthread.h, and there is a pthread library which you should link. Okay, it should be -l pthread. Okay, so you remember that -lm, right? -l math. Similarly, it should be -l pthread, and we'll have a look at how to use this library in the next lecture. I'll show you some code and show you how two different or three different sections of code can execute simultaneously. Okay, that is it. Any questions? So we
Sir,
go ahead.
sir, what do you mean by communication between threads?
Let us say you are let us say the case of our WebEx. Okay, so there is one let us say there is one particular thread which is managing the buttons on the interface, right? Now if on the interface I click on the mute button, what should happen? The voice that is being transmitted by one thread, it should stop, right? Because I have muted myself, right? So even though the UI buttons are managed by thread X, and the voice transmitting is being done by thread Y, there has to be communication between thread X and Y at certain times, right? So because thread X needs to tell thread Y that you should stop sending voice right now because the user has muted him or herself, right? So there needs to be a way to communicate, because these threads are completely independent of each other. They do not share the variables and the code. There is some common way, there is some common place within the process memory block where they can set a flag. Okay, they can set a variable there which the other thread can read. So this way you can communicate. We call them shared memories. Okay, the concept is known as shared memory. So you can create shared memories which can be shared by different threads, and they can use it for communication. One can write it, the other can read it. Okay, and this is the an example of communication where you would like it is what I just told you. Is it clear?
Yes, sir.
Okay. Any more questions? So all these things are, I mean, you are going to learn all these things later. I'm probably rushing you guys to know these things in the second semester itself. Maybe I'm a bit harsh, but it will be very helpful for you, because you'll have so many system building skills right at the end of the first year itself, that from here onwards you can actually start working on projects. That is the idea. Okay, so multi-threading is one. Even though you don't know most of the details of threading, you might actually, there is a risk that you might get stuck into certain problems which you are not able to resolve. So that is why keep your multi-threading applications to bare minimum uh, things. Okay, don't try to make uh, things that are too complicated, because I have not taught you many concepts associated with threads. Threads are they are a delight to use, but they can also very easily turn into nightmares. So please use them very lightly as of now. Okay, don't use them for something very complex, because otherwise you'll scratch your hair. It's so difficult to debug multi-threaded code. So but I want to teach you this so that when you actually read all these things later on, you'll already have a background. Okay, so when you'll know about processes and threads in operating systems, you'll already know what they are. Anyhow, any queries, any questions? So we need to have an extra class this weekend. Sorry, I got vaccinated on Saturday. I thought I'll be fine by Sunday, but it didn't work that way. I had really high fever, 102 degree Fahrenheit on Sunday. So I just could not prepare the slides. So because of which we lost a lecture. So this common lecture should be better, should be more fun. I'll show you some code. There'll be less number of slides and more amount of code. So I hope you guys will enjoy it. So we have to do it sometime in the weekend, Friday or Saturday in the evening time. Who is going to take the responsibility of uh, floating a sheet? I know I force you guys to answer to so many questions, but I think that is the best way to democratically find out a way. So who will prepare the sheet? No one. Okay, good, Shaurya. So please send a sheet to a form, actually not sheet. Send a form to everyone to fill up some time slot. I'll need something on Friday evening or Saturday evening, whichever is fine, and we'll see actual multi-threaded code on that day. Okay. Okay. Thank you, guys. Bye.